Hi, my name is Milos Baskic, and this is my demonstration of the latest implementation of my CSCI E95 compiler. So first of all, looking here at the code, which I will be using as one of my test cases, we will go through all of the stages of compiling the code and analyze what the compiler does at each step. And next, we will look at the output MIPS assembly code and all of the optimizations which I have implemented. And lastly, we will see how the optimized MIPS code compares to the non-optimized MIPS code before running the optimized version, observing the output, and whether it matches our expectations of how the source C code should behave. Cool. So looking at the first stage of the compiler here, it takes the input text, or rather the input code in this case, and it breaks it down into the biggest recognizable components. So in a lot of cases it could be a single character, or in the case of strings, for example, it could be several characters encapsulated with quotation marks, and it assigns to it an appropriate value, an appropriate type, and also where it was found in the source text. And now, just for the sake of readability, we're going to copy paste the output of the next stage, the parser stage, and copy paste it into an IDE. So comparing the output of the parser stage on the left here and the original code on the right, we can see that logically this is the same code, with the exception that white space is ignored and all of the formatting is done by the parser itself. And then here, just for demonstration, on the left side is a diagram created by one of the TAs for this class, Mark Ford, which is a tree structure, or AST, which represents the code in a slightly different form. And this is sort of how it would compare to the output text we have on the right here from the parser. So you can see that a function definition might contain a compound statement, and then the compound statement might have a statement list, and then within a statement list we might have a declaration of sorts. And although this is not the AST for this specific segment of code, this is the type of data structure that will later be used to generate the IR. And now looking at the IR stage here, we can see that we finally reach something which actually looks like some instructions, and we already have something like register allocation happening here, or rather register assignment. And if we look into it, we can actually also see how it corresponds to the code that we saw previously with the exact same structure. It's calling the print statements first, all within main. So we can now already imagine how this is going to translate into MIPS assembly code. And lastly, looking at the MIPS code here, we can see that it translates pretty much one-to-one from the intermediate representation into the MIPS code itself. We can see that we are once again inside main, and here are the print statements that we saw earlier in the C code and then in the IR itself. And this is now ready for execution. And although this was shown briefly in the introduction to this video, it is now interesting to go back to the program itself, now that we have looked into the individual steps a bit more closely, and actually see what the output is and whether it is what we expect it to be. So first of all, if we run the program, we get the prompt and the header here. And then we can also see how it compares to the actual C source code and whether it behaves as we would expect it. So here's the header, here's the prompt, and this is the buffer into which we will read the user's reply. So if we go hello, that should read it, and then it should ask for key. Now, because we're using the Caesar cipher, the key we enter, in this case let's say 3, will shift all of the letters either forward or backward in the alphabet, depending on which option we choose here. So if we choose to decrypt first, it will increment everything by 3 first and then decrement it. And then if we choose to encrypt first, it will decrement and then later increment to show us the original message we entered. So we can see here that we do get EBIIL, which corresponds to hello. And if we were to rerun this and choose the second option, we would first see, if we use this as input, we would first see hello as the decrypted string, and then our encrypted string below that. So now, really briefly going into some more specific features, like for example calling user-defined functions, we can see a very, very simple example here, and we can see the generated MIPS code, and how exactly would call the function. And we can also notice that because the function in question does not use T registers, no T registers are saved nor restored before or after the function call. Whereas looking at the function itself in MIPS code, we can see that all of the S registers are always saved and they are also always restored. And now running this code, we can see that if we enter the number of terms, we do in fact get all of the Fibonacci numbers within that number of terms. And just for some additional variety, here is a program which calculates the prime numbers between two specified integers. So if we enter 0 and 50, these are all the prime numbers between those two. And so coming to one of the more interesting parts, we come to the IR to IR optimizations. Here they all are, all in all, 6 stages. Lovely. So for the most part, it is just a matter of reducing the number of MIPS instructions, or rather IR nodes. So if it is possible to combine two specific IR nodes into one, that is done by these functions here. And then later, once again, because very often it is possible that one optimization level can produce opportunity for possible future optimizations, so a double run can actually catch quite a few more cases than just a single run. And now coming to the most specific optimization in my compiler, this stage optimizes strings specifically, or rather the printing of strings. If they are printed one after another, it combines all of them into a single large string. It gets rid of the unused strings and only performs one system call whenever possible. And for specific coding styles, including my own, this is actually proven to be quite beneficial. And now comparing the unoptimized and optimized code, we have the optimized MIPS code here on the left and the unoptimized MIPS code on the right. First of all, we can immediately spot that the strings were combined into longer strings if they were sequential, and the unused strings were discarded, so we are not wasting any space. But we are saving a lot of system calls here. So you can see this is all of these system calls here are used for printing the header, and only here does the logic start. Whereas here we were able to combine all of those header print strings into one single system call, which only has 3 instructions in total, because we could also combine the load address and the OR instruction. And if we go to the bottom of this very quickly, we can also see how the numbers compare. I did not find a reliable way of testing the times because Qtspim is an emulator, but we can see how much code we've removed. And here are some rough numbers for the other pieces of code I've tested using these optimizations. And with that, I have pretty much covered all significant aspects of my compiler. Thank you for your time. I hope you enjoyed watching this. If you have any questions and you're watching this live, feel free to ask me in the upcoming 5-minute period. Or if you're watching this later, feel free to also just contact me on the email listed on the screen now if you have any questions. Thanks for watching.